Hi, everyone. Thank you for coming. My name is Dominic. I'm the founder and CEO of a company called MemGraph. And today I'll be giving you a talk on why the future of graph databases will be in memory or in memory centric, what we've been hearing about today. So before we start, I wanted to tell you a little bit more about MemGraph, which was basically founded almost a year and a half ago. With basically one very simple mission to become the graph database for the real-time world. So we all know very performant, successful graph solutions that large tech companies like Google, Facebook, Amazon built, custom built for their own purposes. But so what we've seen so far is that basically graph databases in general have been struggling to achieve these levels of performance. And so you can basically see the market as custom built, not extensible. You cannot use it for anything else, but achieves very good performance. Or you can see like graph databases on the market right now, which can be used more or less very simply. But you cannot achieve the right performance for all of the use cases that you want to do. So we basically found a MemGraph with a vision where we can bring these two together. And basically our design goals behind MemGraph were three things: speed, scale, and simplicity. I'm going to tell you a little bit more about that right now. So in terms of speed, we wanted to make it low latency, high throughput. For achieving very low latency, we of course had to go in-memory route. We also are compiling some of the basically query plans to make it run as fast as possible. And for more complex queries with more complex traversals, we can actually make use of multi-processing, multi-threading, where you can basically run your query in parallel and then aggregate the results in the end. For high throughput, we decided to focus on a really good implementation of multi-version concurrency control, which is basically a standard today. But so we were also using lock-free data structures and highly concurrent data structures. For example, we use lock-free skip lists for our indexes. And that's basically allowed us to scale the throughput linearly based on the amount of cores you have. The second point is scale. So basically, we wanted this to scale to real-world data sets. And that can be a problem with in-memory. And that's why we're doing basically two things. One is we are building distributed, fully sharded graph with dynamic graph partitioning. Right now it works only on a single machine, but this is coming later next year. And also we're basically doing what the entire keynote was about, basically optimizing between efficiently using disk and efficiently using in-memory storage for whatever the task is necessary. And we also wanted to do simplicity. That's one of our core beliefs, that graphs should be as simple as possible. You don't have to be a graph expert, so we're basically encapsulating all of the algorithms, all of the searches, and everything what you want to have, and we're exposing. We're basically exposing a very intuitive language called OpenCipher for everyone to use, and we're hiding all of the algorithmic complexity behind that. So I wanted to share with you something. A little bit about the architecture, how we've built this. So we basically went on and fully rebuilt the graph from the ground up. So basically everything is custom built by us. So we're basically build the in-memory native graph in memory with multi-version concurrency control and using skip list, like I mentioned. We're using snapshots, write-ahead logging for persistency. So definitely, in case of a power loss, your graph is persisted. I have toggle this, but I know. We're also, so our query language, our transaction engine actually supports ACID transactions, whatever that means in the graph world. But basically, you get the snapshot isolation, everything you would expect from a database that's running in production. Our query engine is using OpenCipher query language. We do a lot of query planning to execute the queries as efficiently as possible. And then we start with an interpreter, and then we have compiled plans, which we basically do with just-in-time compilation. This is very early with the just-in-time so far. Most of the things are running in the interpreter, but that's also coming next year. And we basically reimagined the networking as well to be able to support the high throughput of the query engine and the storage engine. And we're using Bolt protocol. So all of the applications currently built with Bolt protocol and OpenCipher query language work, which you might be familiar with a graph database called Neo4j, which basically has the same things built. So they, with a bunch of other companies, started standardizing the protocol and the query language, and we basically jumped into the ship and started implementing all of the things. So I usually am pretty wary of talking about the performance benefits, benchmarks, and stuff like that, because your mileage may vary. It all depends on the use case and stuff like that. But basically on the LDBC social networking benchmark, which is basically a standard way which all graph databases are trying to compare these days. So we tested ourselves against Neo4j, since we basically are one-to-one mapping of we can do one-to-one mapping of the queries. So we achieve between 5 and 20x improvement in latency on most of the queries, because most of our queries run in microseconds or single-digit milliseconds. And we also have a couple of benchmarks which we are using with customer data. We are achieving basically 20 times the throughput when you're balancing reads and writes. But where we really shine is when you have a lot of concurrent writing to the database. So for write-heavy workloads, we can achieve 50 times or even more. So I wanted to tell you about the challenges that we're also having, since this is, oh, this is not showing well, but I'll read it through. So basically, high-performance data structures usually have a higher memory footprint because you have to have some control structures and stuff like that. So it's always the trade-off between basically optimizing for performance and optimizing for the memory usage. But I think that a pretty good balance can be achieved, and we're still have some work to do to reduce the memory footprint, but basically we want to keep the performance as it is. One big problem with graphs, because naturally graphs are very dynamic random structures, is that we don't have cache locality. So we have more than 90% of cache misses, and we can go around that problem by cleaning up things and getting things aligned into the memory, but that's generally a big problem with random structures. And also garbage collection, since we're using multi-version concurrency control, so cleaning up old versions which cannot be seen by any transaction, also needs to take place. And usually, I don't know how many of you are familiar with the intricacies of building lock-free stuff, but lock-free data structures usually also have a lot of garbage collection that needs to be done in order to achieve consistency. And highly concurrent code is very difficult to debug. So basically, we had to reimagine the continuous integration process that we have. We're running like a battery of different tests, from the basic unit tests, from the integration tests. So we have synthetic data sets and synthetic queries. We have customer data sets, we have customer queries, and we're also doing long-running stress tests, which are basically running weeks at a time and trying to figure out if there are any memory leaks and any like lost memory in the lock-free garbage collection process and stuff like that. So we found a few, still trying to find a lot more, because you can never prove that there are no bugs. You can just find a bug. So it's always worth testing for them. And one other thing which people usually don't take into the account, since we're a production database that needs to guarantee some level of performance, we need to keep that performance consistent or better for our customers. So we do full regression testing. So we have a lot of benchmarks that we do with both our synthetic code and data sets and our customer code and customer data sets. So on every commit, basically, we run all of the tests and figure out if a person committing is basically degrading performance somewhere. And then we can decide if that's something that we're allowing or it's just an error that can be easily fixed. And some of the limitations of the current implementation that we have are, if your data set doesn't fit in memory, basically you're out of luck. But graph sharding and offloading to disk will help with that, and that's coming mid next year. So it'll be here soon. And it can still be expensive to have a lot of RAM for a lot of data that you are not using. So for example, if you have a lot of properties which you're not filtering on, but you want to retrieve them when you have the results, it might be better for people to have only the graph structure in memory and then actually storing the properties of a particular node or a particular relationship on disk, basically cached in memory by like least recently used, something like that, with people, basically depending on the use case. So I wanted to talk about a couple of use cases that we are seeing with some of our early adopters, early customers. So basically one of the really obvious ones, and what a lot of people are doing with graphs, is real-time recommendation engines. So basically anything from product recommendations, content recommendations on online shops, movies, whatever. If it looks like collaborative filtering, graphs are a very good fit. And especially with our solution, so what we enable customers is to push thousands of updates per second into the graph, and then do real-time collaborative filtering style search on top of the graph without degrading the performance. So you can always have everything ingested and have everything running smoothly. The other very interesting use case that we're doing with a customer are real-time credit card fraud detection. So basically you have tens of thousands of credit card transactions per second, and for every transaction you have, basically you also, on top of these credit card transactions, you have a lot of updates to the graph which are running in parallel with the credit card transactions, which basically update the state of the graph, the state of people, linkage, connections with their addresses, phones, the entire KYC knowledge graph. And for every transaction, we basically run a real-time analytical query. We try to expand as much as possible and as wide as possible to cover basically depths between like 25, 30, 35, or even more. And it has to be done in less than 100 milliseconds because one really good thing is if you can do that, then you can achieve no chargebacks. So you can decline the transaction as it executes. Because, for example, many of the current fraud detection systems actually allow the transaction to go through. Then when the analysis is finished, everything gets reversed, and that costs money. So if you can do that before, that saves a lot of money. One big case that we're working on with Fortune 500 bank, basically data lineage. After the financial crisis, there's a lot of things the basically the Basel Committee of Banking imposed on banks to need to keep track of. And you need to keep like a 5-7 year history, stuff like that, of every change that was happened on all of your data. And it becomes really difficult to do that if you're doing that across more than 4,000 systems, which all of the people in the bank are using simultaneously. So the idea is to build a large MetaGraph on top of basically all of your system, which tracks changes, like GitHub tracks all the commits to the repository. And so you can very easily have effortless compliance and also eliminate inefficiencies with information sharing and stuff like that. Inside, and it can be really demanding, a really demanding use case. If you want to do it in a relational database, whenever something changes, a new type of data comes in, a new transformation, you basically need to migrate the schema, and you ended up with so many tables and end up doing so many joins that it's not easy to work with, and is also not performant. And dynamic graphs are actually the perfect data structure for that, because they offer you you can very easily add different types of nodes, different types of relationships, and store different properties for every node. With another business case, which is impact analysis and root cause analysis. So we're actually working with a telco to map out their network infrastructure. But you can imagine that this being used on an energy distribution company or anything that tracks infrastructure, and it's basically dependent. So if you can map out all of the dependencies, for example, between network equipment, routers, everything, you can better plan for high demand and when you have high volume of things coming, and plan for redundancy. And even when things break, what you can do is you can track every issue to its root cause. For example, our customer is having problems with when something breaks, they get 1,000 alarms, and then they get a dozen technicians randomly poking around trying to figure out where the failure is. And if you can direct them to the right point immediately, that's basically saves them a lot of man effort and a lot of downtime that they would usually have. So these are the 4 most interesting cases that we've seen so far. And I would like to finish the presentation with basically talking about what's the future of MemGraph. So we're doing a lot of improvements. We're still a very early company. I existed for a little longer than a year, almost a year and a half. We want to continue making performance improvements, so we will continually improve our planner, just-in-time compiler, stuff like that. We want to reduce the memory footprint because memory is still expensive, but it's going towards being less expensive and combining all different sorts of memory. And the biggest thing that we're working on right now, we have working implementation, but it's not ready to push out to the world. It's basically sharding with dynamic graph partitioning. So what people usually do is base their solution on top of a key value store, on top of something else. And because the key value store is inherently distributed, they call their graph database distributed. But this is not working when you need to scale to hundreds and thousands of machines. So what you actually need to be doing is dynamically repartitioning, always shuffling around nodes and edges, basically tracking how the data is being laid out, what are the queries, and how to improve the performance of the queries. And in only that way you can achieve like general sharding strategy, where your use case basically, your performance on your use case gets basically better over time as you use it. High availability replication is actually coming this month. So this month we'll also be able to push production use cases. And enterprise grade security is basically coming also in the following months. So for all the compliance stuff for the banks and different organizations that require these things. We will be able to offer that as well. And I want to finish by taking the questions from the audience, but I want to first tell you that we're basically opening up early access. We launched a couple of weeks ago at Strata Data Conference. And so you can now basically sign up. You get the access to the portal. You can download MemGraph, see documentation and everything you want to have. Please don't hesitate to contact me if you have any questions, so if you would like to learn more. And now I'll be taking questions from the audience. Yes?
High availability is my favorite topic. Could you elaborate a little bit on this? Is it the high availability inside the data center between the multiple nodes or across the data network? Or what
Yeah, this one is the, so by the end of this year, we'll have only like inside a data center. So the assumption is that your servers are close. But yeah, cross data center is something that we will be working on next year. Yeah, so it's yeah, it's going to be Raft consensus. So it's going to be basically a replicated log with all of the deltas.
But Raft doesn't work over wide area networks.
Sorry?
Raft doesn't work over wide area networking.
Yeah, that's what I'm saying. It's going to be basically inside the data center right now by the end of this year. So this is going to be the first one. Any more?
Your performance stage, what was the baseline?
Sorry?
Your performance, you had a slide of performance.
Yep.
What was the baseline comparison?
It was Neo4j. So this is the improvement on top of a graph database called Neo4j, which is the oldest on the market right now.
So in terms of clustering and distributing the data across the cluster, what are your plans? Like you said, like you're going to do sharding?
Yeah, so it's gonna be real sharding, fully sharded. So it's gonna we're gonna figure out a really smart way of pushing the data initially. Then we'll have basically a black box algorithm that is monitoring constantly the data that's coming in and also the queries that are coming in. So we're generating kind of a heat map for graphs. And whenever you have a hotspot, we basically can break it off, shuffle it around across multiple machines, or even duplicate the data at some point. That's also one strategy that's also very effective, especially if the graphs are not high velocity. And there are a couple of like more things that you can do to basically make it scale well.
So like AC transactions and the other stuff that have to be reworked?
A little bit, yes. A little bit, yes. So it's gonna be consensus transactions, and so everyone's gonna have to take part. It's gonna be a master and basically leaf architecture. So you have masters and nodes.
So multiple masters and some.
Yeah. So it's probably going to be like that. So that's our first implementation. So you can have one master, but for to have fault tolerance, you can have multiple masters, and masters will not hold any of the data. So it's going to be a bipartite graph between the masters and the leaves. So only the leaves hold the data.
You mentioned on commit, you run node tests or performance tests to
Yeah.
see performance was degraded. How long do those take after a commit? Like when do you get your response that they degraded it? And then if you go into elaborate like what it looks like, do you have a separate load testing environment that you run it in?
Yeah, so basically we keep all of our customer data sets and synthetic data sets. So we can actually tune how, we have a lot of benchmarks which we can run in parallel. We mostly use AWS Spot instances, but we have some hardware of our own. So depending on when do we want to get the result, we're basically load balancing and pulling the infrastructure as we need. And we get into our code review environment, we, as soon as the tests are finished, we get basically a ping back, and we have like the entire report of what was better, what was worse, and all of the things that stayed the same. So people, when doing code review, can basically in real time receive feedback from the stress testing and benchmarking. And they can look up things in the code where these things might matter, and they can go into like further debugging and stuff like that.
Do you run the stress tests and benchmarking like nightly or hourly or after each?
It's basically real time. So we do it after every commit, and we do longer. So we do longer testing overnight, and stress tests, which usually take a couple of days to a couple of weeks, and that's what we do before any major release. So basically 24/7 in between.
Continuous testing.
Yeah, continuous testing. Any other questions? If not, then thank you all. Come see me if you want to speak with me. I'll be here for a little while. And if you have to go, don't hesitate to reach me. And be sure to sign up for early access and download the free community edition and test it out in our data set and see how it goes. We'd love to hear feedback. Thank you so much.